then we're going to get a bunch of regions over here. Okay, and we don't know for sure exactly what they look like in the general case, though we do know what they look like for this particular mapping. For this specific mapping, our vector xri plus yrj, it looks like I've been running around with an I there where j should be. Again, for this particular mapping, this vector is just a radial vector straight out from the origin, so that these vectors all point straight away from the origin. I haven't drawn them that way because I wasn't making any assumptions, but now if I want to draw the result of this mapping accurately, these vectors are all going to have to point straight away from the origin, and these vectors, as you can easily verify, are perpendicular to these vectors. So they point perpendicular to the radial direction at every point. So for x equal r cosine theta, y equal r sine theta, this region here maps onto our familiar picture, and I'm going to draw it a little bit sloppily here, but get the idea. Our picture of the polar coordinate plane. For any region within that plane, this vector here is going to be approximately equal to xri plus yrj delta r, and this boundary here, which is actually curved, is going to be approximated by the vector, and it's a straight line vector now, x theta I plus y theta j delta theta. That's this vector. This actual region of the polar coordinate plane, of course, gets wider as we move out, and these vectors don't model the fact that this is getting wider. We evaluate this vector and this vector at some sample point within the region so that it's going to be close to but not exactly equal to the boundary of our polar coordinate region. But in the limit, as delta r and delta theta approach 0, all discrepancies due to evaluation at the sample points shrink to 0. And I should have said the total of all the discrepancies shrink to 0, with the result that the area of our region, the area of our arbitrary typical region, just becomes the cross product, the magnitude of the cross product of this vector with this vector. And I'm factoring out the delta x, delta y, delta r, delta theta. Didn't quite get that in the corner there, but we'll write that out more fully in a minute. For this specific mapping, which we're illustrating here, we can write out xr equals cosine theta, x theta equals negative r sine theta, yr equals sine theta, y theta equals r cosine theta. If we work out this cross product, we find that this area becomes just r delta r delta theta, the area increment that we obtained geometrically before. That is, the cross product is just r. Put these expressions in for the xr, yr, x theta, y theta, do the cross product, and your cross product reduces to r. So that for the present mapping, for x equal r cosine theta, y equal r sine theta, double integral of magnitude of r sub r cross r sub theta dr d theta equals the double integral of r dr d theta. On each increment of delta r by delta theta, we have a corresponding increment of the area in the xy plane, and this integral is just the area of the region 0 less than or equal to r, 0 less than or equal to a, 0 less than or equal to theta, less than or equal to 2 pi in the xy plane. I'll just mention, it turns out that if we calculate the area of this region in the r theta plane, we get 2 pi a. Whereas the area in the x versus y plane is pi a squared, as you can verify by taking this integral from r equals 0 to a and theta from 0 to 2 pi. Antiderivative is r squared over 2, etc., etc. We get this area, and of course that is the area of a circle described by these parameters in polar coordinates. We conclude that this is not an area preserving map, the map that takes our theta coordinates by this transformation into the xy coordinates, and that the area factor increases with increasing r. In the next clip, we'll ask the question, what if the mapping isn't x equals r cosine theta, y equals r sine theta? What if, for example, x equals 2r cosine theta and y equals 1 over 1 plus r sine theta? That is going to give us something besides polar coordinates. This is not going to be interpretable as polar coordinates, in which case we're probably going to want to let r and theta be different letters. For example, x equals 2u cosine v, y equals 1 over 1 plus u sine v. That'll help us avoid confusion with our traditional interpretation of r and theta. But the model is going to hold just as well. We can have a region of the UV plane mapping onto region of the XY plane, and by considering the XU and YV, XU and YU and XV and YV derivatives, we can obtain information about the new region. I really like this camera. It does a great job with audio. Visuals are good, but it does have autofocus, so I don't know at what point the focus blurred out here. But I just said, what if we have a different transformation? Now r and theta can't be interpreted as the polar coordinates in the xy plane, because that's not the right transformation for polar coordinates. We replace r and theta with u and v so that we don't have the polar coordinate connotation, and we're going to consider what kind of region we get in the xy plane if we take a region of the uv plane here and map it using x and y. Rather, map it using this transformation into the xy plane.